Hello everyone. In this video, part 3 of the third visualization of complex multiplication over imaginary quadratic rings, I'm going to just show a couple more examples of this third visualization over the Gaussian integers or over g of I or over the regular complex numbers. In this example we're going to use the complex numbers, the complex number 3 plus 2i or 3, 2 as a vector, or negative 3 plus 5i or negative 3, 5 as a vector. I'm assuming that you've seen the first two videos, otherwise this probably might not make any sense to you. I'm going to use some shorthands here too, shorten up the method a little bit. First I'm going to reflect the first vector or complex number over the real axis to give its conjugate in regards to the complex number or the reflection through the real axis in regards to the vector. And I'm going to take the perpendicular line through the reflected vector or conjugate of the first complex number and through this point, the terminus point of the second vector, or through the second complex number. As we can see, the perpendicular line does not in fact intersect this vector at all. In fact, we're going to have to take the negative of that vector, and Cabri, we're going to use the symmetric function in regards to the origin. But even that doesn't quite get us there, so we're going to have to even take a translation of that vector. Okay. That tells us, of course, that the inner product in the real portion of this complex product will in fact be negative. Okay, the second thing we have to do is we have to define the intersection point between this translate of the reflected vector in this line. And we're going to have to take a couple distances again. We're going to take the height of our parallelogram. I'm not even going to spell out the parallelogram here. So you've seen the other videos, will know exactly what I'm doing. We're going to take the length from here to that intersection point, and of course, excuse the magnitude of this reflected vector, which of course is this magnitude of this vector here. Then we have all the numbers we need in order to calculate our real and imaginary portions ultimately, or inner and outer products. Basically, again, if we set up an axis here with a vertical axis perpendicular, parallel to this line here, it seems pretty evident that this point up here for the imaginary portion would be in the third quadrant. In any case, it's above this line. So that tells us, of course, that the imaginary portion will be positive. If we set up a parallelogram of the sum of these two, you know that the sum would be somewhere over here, and it's pretty easy to see that we'd go counterclockwise. So that makes sense, obviously. So we take this number here, which is the base of our parallelogram. Okay, and we're going to multiply it by this number over here. That distance is going to be our height. And then we find out that the imaginary portion, we calculate the imaginary portion first, as was explained in the part 2 here. In any case, our imaginary portion of our product is going to be 9. Then we're going to calculate the real portion, which will be negative, of course. Set up that axis again, whatever the other explanation I gave in the first video was why that would be 2. You can put the negative sign on either one here. It'd probably be better to put it on the first one, but I've been putting it on the second one here. See, I'm negating the second one here, the 5.27. One way or another, you have to put a negative sign on one of them in order to get a negative result, which is what we want for the real portion. This tells us that, of course, our result is the product of 3 plus 2i and negative 3 plus 5i is negative 19 plus 9, 9i. And in fact, if we check this, you see I've calculated here already, negative 19 plus 9i. You can see it all works out, unless I've made some other mistake, which I'm hoping I haven't. Again, I'm going to employ the same shorthand again on one more example. to just illustrate this method again over the regular complex numbers, or z of I. So we'll do the same thing again. We're going to take our first vector, we're going to reflect it through the real axis, getting the conjugate of that complex number, of course. Then we're going to take a perpendicular line to this reflected vector, or the conjugate, through the point, through the second complex number, or through the terminus point of the second vector, and then basically we have to find, again, we're going to have to take the negative of this. It might be, in fact, a multiple of the negative of this vector here in order to find that intersection point. Again, Cabri uses the symmetry function for that. We're going to have to translate this vector again, and then we find our intersection, and we're going to have to define that intersection point for Cabri. And then we go for our distances again. Distance from this point, okay, to that point. Then we need our distance from here to the intersection point for inner product, and we need the length, or the magnitude, of the second vector. Now we have all the numbers we need, and now we need to do our calculation. Again, we're starting with the outer product, or the wedge product, first, because of course if we draw our axes again through the origin, whatever, parallel to this, and so on and so forth, I think it's pretty clear that this point down here is going to be in the third quadrant, or in any case below this, what would be a kind of superimposed real axis, or horizontal axis, if you will. And so it is going to be negative. So we're going to negate one of the components in it in order to get that negation. So we're going to multiply the base of our parallelogram. Again, if we spelt out the parallelogram, you would find, of course, it would start over here, and the sum of these two would take us somewhere over here. So what would happen is that you'd swing around the points, and there would be a clockwise rotation on it. And we're going to multiply it by the parallelogram's height, by the height corresponding to this side here. It's over there, but it's the same height. You can prove that to yourself, I think. Some of you will just see it because you're very good visually. Okay, and that tells us that the imaginary portion of the complex product of these two complex numbers is negative 18. Now we're going to calculate the real portion, which is also negative, because obviously, just going the opposite way at negative translate, or if you put those axes up again, it's on the negative side. Again, you can negate either component. I've been doing the second one. It might be a little bit better to do the first one. I'm not really sure, but in any case. And so we come up with negative 30 for the real portion. And let's see if that agrees with. So it should be negative 30 minus negative 18i. Yes, negative 30 minus negative 18i for 3 plus 3i times negative 8 plus 2i. Okay, and that pretty much takes care of this method over the Gaussian integers, or over the nominal, normal, complex numbers. For the other imaginary quadratic fields, you need to adjust this method to do it, and I'll have another video probably just about that adjustment in itself, and then another one probably for examples. Okay, that's it for this video.